In the first lecture of this module, we set the stage for life on Earth by looking at the first 500 million years of the Earth's history. To understand life in the universe, we have to look as closely as possible at the one place we know of life in the universe, where it exists on the Earth. Astrobiology is speculating that life might be found on other worlds, like the many exoplanets we've been talking about. But Earth is still the only form of life we can study, so we look at it as carefully as we can. And in particular, we want to know how life arose on the Earth. In other words, was life an accident, a fluke, a freak, or was it an inevitable result of physical processes leading to biology? At the moment, we don't know the answer, but we learn as much as we can by looking at the Earth's history, deep into time. The deepest part of the Earth's history is called the Hadian Era, the first 500 million years after the formation 4.54 billion years ago. The planet soon after formation was a searing molten place, originally with no atmosphere, with no solid surface even, because the rock was molten, and the surface temperature was probably 450 degrees Fahrenheit. The atmosphere at that time was primarily carbon dioxide, with some water vapor and some hydrogen. The light gases, hydrogen and helium, were escaping into space, and there was as yet no atmosphere resembling the one we breathe today. The conditions were indeed hellish, and that's why we use Hadian, from the Greek underworld, for Hades. It's important to recognize that we know very little about this era of the Earth's history, the first 500 million years. And that's because the Earth is an active planet with plate tectonics and geology. If you were to go outside, no matter where you live, and pick up a rock, the typical age of any rock you might find is only going to be a few 100 million years. It's quite difficult to find rocks even 1 billion years old, and very difficult indeed to find rocks more than 3 or 4 billion years old. In fact, there are only a couple of places on the Earth's surface where we can study Hadian rocks, and they include parts of Western Australia and southern parts of Greenland. So, we're talking about an era where the physical evidence is rather slender. However, we have indirect evidence that something quite spectacular happened after the Earth formed, and after it had cooled, and probably after oceans had formed and the atmosphere had formed. And it's called the Late Heavy Bombardment. It's speculated that 3.8 to 4 billion years ago, so 500 million years after the Earth formed, the planets, including the Earth, underwent a period of heavy meteoric impacts that's been called the Late Heavy Bombardment. It connects with an idea we've talked about in an earlier module, where the chaotic solar system included the rearrangement of the positions of some of the giant planets. Wholesale migration or movement of the giant planets would trigger a large increase in the flux of rocky objects heading towards the Earth, and therefore an increase in the bombardment rate. It's also theorized that a lot of the water on the Earth arrived not only during its formation era, when the Earth was built from smaller pieces of rock, but also in the late heavy bombardment, when water could have arrived in frozen form on rocks from the asteroid belt or even further away. At the moment, the source of the Earth's water, the water in our oceans, is somewhat controversial. One theory holds that it was deposited after formation by rocky and icy material bombarding the planet. This is called the late veneer theory. But there's another theory, not fully accepted by most geologists, that the Earth always had water deep in the interior, in the mantle, and eventually that rose up to the surface to become the oceans. It's very hard to resolve these different ideas, given the lack of physical evidence. However, lunar rocks brought back by Apollo astronauts in the 1960s allow scientists to estimate when the late heavy bombardment history happened. And that's because the lunar surface is unaltered by erosion or plate tectonics. And so the cratering record does indeed show a spike in cratering at around this time, just before 4 billion years ago. Also, Mars cratering history shows a similar spike, although Mars has had active geology in its past, and the evidence is less clear in these cases. But the evidence for late heavy bombardment has been erased since that time, of course, by weathering and geological processes over time on the Earth. So we cannot use any cratering history of the Earth to support this idea. Instead, we have to look deep into the Earth to the geology of the Earth. Remember that the deepest hole humans have ever dug in the Earth is a mere pinprick in the crust, reaching tens of kilometers down, and the Earth being thousands of kilometers across. So once again, inference is used in geology by the way seismic waves transmit through the planet and bounce across the planet and refract, just as other waves might do through a medium. So we look at the geology of the Earth, and it's the science that looks at the internal structure of the Earth and tries to understand the history of the Earth and the processes acting on it. We've put together a pretty good geological history of the Earth, where the most uncertain parts are that first 500 million years. But we can learn a little about the potential for life on exoplanets by studying what happened on the Earth when life was first forming. The geological processes of interest on the Earth and any planet like the Earth are, of course, erosion, which is when wind or rain or other processes loosen bits of rock and move them from one place to another. On the Earth, with its wet atmosphere and its winds and its oceans, driving water into the atmosphere and then back down onto the surface in the oceans, there's a lot of erosion. Features are eroded on timescales of hundreds of millions of years, but on that timescale, entire mountain ranges can be degraded. Weathering is another process, which is caused by changes in temperature that make rocks expand and contract and shatter them, and essentially break them down, from full rocks down to pebbles, even to sand grains. Wind and rain and snow wear at the surfaces of rock continuously, and while this process is imperceptible to us on human timescales, on geological timescales of millions or even billions of years, it again can dramatically alter the surface of a planet. The final process that takes place is plate tectonics, and that's the fact, discovered about a half-century ago, that sections of the solid rock that make up the Earth's crust are actually in motion. It's not rapid motion. I think the most rapid plate motion is something like a fraction of a centimeter per year. But these plates are continually moving by these small amounts, and over a period of time, it can add up to substantial motion and create huge stresses at the interfaces between the crustal plates. These plates collide, they grind past each other, they slide above and under each other, and many of the most dramatic situations on our planet, such as volcanic activity and earthquakes, occur where this takes place. There are incredible forces unleashed in plate tectonics and in crustal motions, and these can completely transform the history of the planet and the surface of the planet, the way it appears from space over time. We think that all of these three processes will take place on Earth-like exoplanets. We can look at examples of geological processes that take place on the Earth in places perhaps that you're familiar with. For example, geological studies have revealed that the Grand Canyon was created by the Colorado River eroding the land over millennia. Perhaps shocking to someone who's seen the enormity and the grandeur of the Grand Canyon is that this entire process of carving out deep chasms, thousands of feet deep, only took some millions of years, not billions of years. Also near the area where I live, the Zion National Park was a vast desert with sand dunes hundreds of feet deep a quarter of a billion years ago. And in a place that I visited a long time ago, in the northern part of Ireland, there are 40,000 columns at the Giant's Causeway that are the product of an ancient volcanic eruption. They have a bizarre hexagonal pattern that is due to preferential forces and stresses in cooling magma. It's sheer evidence of volcanism at play in this island off the coast of Britain. The science of geology, combined with radiometric dating, which is the dating of rocks and materials by the rate of decay of radioactive isotopes within them, allow us to infer otherwise inaccessible timelines. This process of radioactivity is the key tool for understanding the geological history of the Earth, so we'll talk about it a little more. In radioactivity, an unstable heavy atom can change by spontaneously emitting an alpha particle, which is 2 protons and 2 neutrons bound together from its nucleus. If the number of protons changes, the original element becomes a different element, for example, radium turning into radon. If only the number of neutrons changes, the resulting nucleus becomes what's called an isotope of the original element. The original atom is called the parent isotope, and the new atom, after radioactive decay, is called the daughter isotope. Sometimes radioactivity from one state leads to another radioactive state, so there can be a second stage and a third and even a fourth before a stable atom is reached. So we have chains of radioactive decay. But each radioactive transformation occurs at a steady rate. The rate at which a particular atom decays is measured in half-lives, which is the amount of time it takes for 1/2 of the atoms in the sample to decay. This is a number fixed by nuclear and atomic physics and is invariant across the universe, and certainly in the samples we've studied. So measuring the parent and daughter isotopes and their ratios in a rock where we know when those ratios were fixed by its formation can lead us to age-dated rock. By choosing the appropriate radioactive isotopes, we can probe different timescales, such as the billion-year timescale, or the few 100-million-year timescale, or the even shorter timescale. For human civilization timescales, we use radioactive carbon, which has a much shorter decay life. So the radioactive half-life is the determination of how long it takes a sample or a collection of radioactive atoms to decay. Intriguingly, radioactivity is a truly random process in the quantum sense. So if we stare at one individual radioactive atom, we could not predict with any certainty, or even at all, when it will decay. But if we have an ensemble or collection of a large number of those atoms, we can predict with very high reliability when 1/2 of them will decay. The analogy is of a plate of popcorn or pan of popcorn burning on a stove. If you do the experiment over and over again at a fixed heat level, you can predict quite clearly how long it'll take for 1/2 the kernels of corn to pop. That's the radioactive or popcorn half-life. But if you stare at an individual kernel, you probably couldn't predict, and you couldn't in practice when it would pop. That's a reasonable kitchen analogy for what's going on with radioactivity. Consider the example of a material that contains an atom with a half-life of 1 million years. If we begin with 20 grams of that material, after 1 million years there would be 10 grams of the original radioactive material left, and after 2 years there would only be 5 grams, half of 10 grams. We can use the radioactive half-life of a particular element to calculate the age of matter that contains that element. And this is routinely done, and it's how we know the age of the Earth is 4.54 billion years with a very short error or uncertainty in that of perhaps only 1%. How far can we push back in the history of the Earth by measuring rock samples and their ages? An extraordinary discovery of a decade or so ago was called the Jack Hills zircon samples. The Jack Hills region in Western Australia is one of the places where the very oldest rocks on Earth can be found. I've been there once a long time ago. It's a brutal desert, hot even in the Australian winter, and in the summer intolerable, much hotter than Tucson where I live. The radioactive method was applied to crystals found in this Jack Hills region, and the age of these crystals, using the radioactive half-life method, was confirmed to be 4.375 billion years with an error of only 6 million years. So these crystals formed in the first few 100 million years of the Earth's existence. These are tiny, barely bigger than a grain of sand, extraordinary samples of the very early Earth, soon after the crust actually solidified. There's a critical detail provided by these very old samples of the Earth's crust. Chemical analysis of these samples indicates that they were formed at a moderate temperature in the presence of water. So the Earth was not an unspeakably hot place when these crystals formed, even though it was within 150 million years or 200 million years of the formation. Also, that indicates that stable bodies of water, or oceans, or at least shallow seas, existed at that time. So we have from these tiny little samples of the early Earth an indication that the stage had been set for life within 200 million years of the Earth's formation. Again, in a situation where there was no oxygen in the atmosphere, would have been unbreathable to creatures like us. So scientific analysis of these crystals shows clearly they formed in the presence of water, and they were found embedded in sedimentary rock, which also is deposited in a liquid, in this case water. Sedimentary rock is produced when moving water deposits particles in an area over a long period of time. The sediment is then compressed by geological forces into solid rock over millions of years. So we are starting to piece together the geological timeline of the early Earth. And the zircon crystals tell us two critical details of the early Earth: that there were solid rock surfaces and water surfaces on the Earth 4.4 billion years ago. It's an extraordinary result because it indicates, since carbon was available and energy was available, that all the ingredients for life were present then. So using radiometric dating in the science of geology, we can learn about these almost inaccessible eras in the Earth's history. It's amazing that we can reconstruct the early history of a planet as large as the Earth from a crystal that's smaller than the little nail on your finger. So we have the geological timeline, and if all rocky planets have a similar formation process, then studying the geological history of the Earth should give us an understanding of other rocky planets as well, including those many exo-Earths that have been found around other star systems. Understanding the geology of the Earth helps us to understand its history. Geological processes have changed the Earth dramatically over its history due to processes of erosion, weathering, and plate tectonics. We measure the early Earth in terms of time by radioactive decay, a physics process that allows us to measure the half-life of atoms and then project that into samples of rock formed at different times. Radioactive decay is how we know that the Earth is 4.54 billion years old, with very little uncertainty in that number. Scientists have found rocks dating back from 4.4 billion years. Not rocks, actually crystals that formed in the presence of water. And that indicates that there was a solid surface and stable bodies of water within 200 million years of the Earth's formation. In other words, the stage was already set for life.